Hello, Mr. Price here, and this is the 7th video of the January 2006 M2 paper, and this one will be on question 7, and this one is all about powers and work dones and energy. Let's have a look. So, we have a gentleman here that's riding a bicycle at a constant speed of 12 meters per second. So constant speed, so acceleration equals 0 is implied here. And on a horizontal road, so he's not working against gravity in any way, and he's working at a constant rate of 300 watts. So this rate of energy is power. So his power is 300 watts. And the entire mass of this whole body is 75 kilograms. And we want to calculate the wind resistance against Marco and his bicycle. So, we know that we've given power, so we're going to give ourselves a little bit of help here and say that power is a work done over time, which is also a force times a distance over time, which therefore is also a force multiplied by a velocity. So, we're told that his power is 300. So, power equals 300. And his velocity is 12 meters per second. So substituting this in, we have power equals FV, 300 equals F lots of 12. So the force that Marco is applying is 300 over 12, which is 25 newtons. Okay. Now, if we just quickly model the bicycle here, so that is how much force that he is generating. There's his weight. So we know that the acceleration here is 0. So therefore, at the moment, we have a resultant force of 25 newtons, so there should be an acceleration. So obviously there's going to be a resistance force there, which has to be equal to 25 to cancel it out. So R is also equal to 25 newtons. And that's job done for part I. Okay, for part 2 now. We have another biker. This time we have Nicholas, and he's riding his bicycle at the same speed as Marco, directly behind him. And Nicholas experiences 30% less wind resistance than Marco, and we want to find out the power of Nicholas. Okay, so here, let's just quickly model what's happening here. So Nicholas has a force, he has a resistance which is 20% less, 30% less. So this is going to be 0.3 lots of 25. And he's travelling at the same speed as Marco, which was 12. We want to find the power. So first we're going to need what this force is, which he's still not accelerating. So that should be 0.7. Because there's 70% No, that is 0.3. No, it is 0.7, sorry. That should be 0.7 because he's got 70% of the total resistance. So F equals 0.7 lots of 25, which is equal to 17.5 newtons. So power equals force times velocity. So power equals 17.5 lots of 12. So we should get a power of 210 watts. Okay. And that's for part 2. Okay, for part 3, we're going to assume that Marco's wind resistance is unchanged. So, the two cyclists arrive at the bottom of a hill, which is at an angle of 1 degree to the horizontal, and Marco increases his power output to 500 watts. Assuming Marco's wind resistance is unchanged, calculate his instantaneous acceleration immediately after starting to climb the hill. Okay, so here we're going to do a force diagram of what's happening to Marco. So I'm not going to rotate it up, I'm just going to keep it in a horizontal plane. So he's still generating a force here, and there is still resistance. And his wind resistance is unchanged. This is still 25 newtons. Okay, but now there's an element of his weight acting against him, which is 75 G at an angle of 1 degree. Okay. And we want to find his instantaneous acceleration. So we know that Marco's power is 500 watts. And power is force times velocity. Okay. And his speed hasn't changed yet because we're looking for the instantaneous acceleration. So Marco's force that he exerts at the bottom of the hill is 41.6 recurring newtons. So that is the force that he is producing. So this is 41.6 recurring newtons. Now, obviously there's going to be a resultant force which we should calculate. So the resultant force is equal to 41.6 minus 25 minus 75G sine 1. So it should give us a resultant force of 3.8386 newtons. So then, using F equals ma, sorry, I'll put the wrong thing in here. So using F equals ma, with the force being 3.8386 over 75 equals the acceleration 0.0512 meters per second. Okay, let's look at part 4 now. So Marco's going to reach the top of the hill at a speed of 13 meters per second, and he freewheels down the hill, which is 200 meters long, and that hill is at a constant angle of 10 degrees to the horizontal, and he experiences a constant wind resistance of 120 newtons, and we want to calculate Marco's speed at the bottom of this hill. So let's model what's happening here. Here's our hill. At an angle of 10 degrees. Okay, Marco's going to be here, and we know that he's already travelling at a speed at the top of the hill of 13 meters per second. And know other bits and pieces as well. So let's just quickly do a more simplified version of what's going on here. So he has gravity working in his favour, and he's still 75g. That's an angle of 10 degrees to the vertical. And is he producing any force? No, he freewheels down, so there's no other force acting on him other than the resistance, which we're told was 220 newtons. Okay, so we're going to need the acceleration of this particle here. So resolving down the hill, we have 75g sine 10 minus 120 equals ma. So after some expansion, we should get that A is 0.102 meters per second. Now we have the acceleration, we can start to use that. Now we know that this distance in total is 200 meters. So U equals 13, A equals 0.102, we're resolving down the hill, is got to travel 200 meters, and we are being asked to find his velocity at the bottom of the hill. So v squared equals u squared plus 2ax, v squared equals 13 squared plus 2 lots of 0.102, lots of 200. V squared should then be 209.8, so that gives us a final velocity of 14.484 meters per second. And that is job done for question 7.